So today's video is going to be part 2 out of 5 in the review of Unit 7 from AP Physics 1, which is torque and rotation. Today we're going to be talking about introductory rotational kinematics. Yesterday we talked about torque, and so today we're going to go into some motion that comes with torque. So I will have linked in the description the Google Doc of everything I talked about today, and hopefully you guys enjoy. If you do, make sure to leave a like and subscribe. It is really helpful. And yeah, hopefully you guys enjoy. So let's start off by talking about what is rotation and what is revolution. So when we talk about revolution, we're looking at an object going around another object. So for example, if we take the sun, I'll just say S, and then we take Earth, okay? Every year, Earth revolves around the sun to make a full revolution, to make a year, right? So that's a revolution, right? We have two objects. We have one object going around another. Now, what is rotation? Well, rotation is the spinning of one object about its own axis. So again, if we take the Earth and the sun, if we take the Earth, every day the Earth spins about its own axis, and that makes a day, right? That's why we see, the sun for 8 hours a day, because the Earth rotates about its own axis. It's not rotating about the sun in this, example. It's revolving around the sun, obviously, but it's rotating every day. So that's something important to understand when we're talking about torque rotation, to understand the difference between revolution and rotation. So let's talk a little bit about the differences between linear kinematics that we learned in Unit 1 and rotational kinematics that we're going to be talking about now. So first of all, what is angular displacement versus linear displacement? Well, angular displacement, which we'll call theta, is going to be the angular amount that an object moves in a given amount of time relative to one full rotation. So it's usually measured in radians, where one full rotation is going to equal 2 pi radians. It can also be measured in degrees, where one full rotation is going to be 360 degrees. So the difference between angular displacement, theta, and linear displacement, which we can call either d or x, I'll call it d, is that angular displacement is relative to an object's full rotation. So while linear displacement is the actual distance moved by an object during rotational or linear motion, the theta, the full rotation, it's relative to a full rotation. So if we look at this, if we have an object that's this big, right? We have a circle, and we're going to be rotating, right? Let's say this is a tire, okay? And let's say that we're going to be talking about a dot right here where it's going to go, right? If we have now gone through a full cycle, or not a full cycle, I should say, if we've gone through a scenario and now the dot is here, it's gone this way, right? Then we've gone pi radians, right? Or 180 degrees, because we've gone half a full rotation. And we've also gone some amount of linear displacement, right? Now, let's say we take a smaller tire, right? Let's say we take this tire with this dot, and then we take this tire again after a scenario, and the dot is here. It still only has an angular displacement of pi radians or 180 degrees, but the linear displacement is less. Obviously, it's traveled less actual distance, but the linear displacement is the same because relative to its center, you could say, it's moved the same distance in degrees. So that's important to understand the difference. So now, how do we get from linear displacement to angular displacement? Well, d, which is our linear displacement, is going to equal the radius of these circles, so r and then r, times the angular displacement. So let's say our angular displacement is pi radians and our radius is 1. Then our linear displacement would be 1 times pi radians, so it would be pi meters. Okay? So that's important to understand. So now let's talk a little bit about velocity. So angular velocity, which we're going to call w, it's basically just a w, is how fast an object is moving relative to a full rotation. So again, this is relative to a full rotation. It's measured in radians per second. And something we need to understand is that, similar to torque, counterclockwise is going to be positive and clockwise is going to be negative. So when an object is moving in the counterclockwise direction rotationally, it is moving positive, and when an object is moving clockwise, it is moving negative. So this is different from linear velocity, obviously, where it's the actual speed an object moves. So it's going to be, how fast it's going in this direction. With rotational velocity, it's how fast it's moving in this direction, right? So if we want to get from velocity to angular velocity, all we have to do is, just like we did for displacement, we're just going to do the velocity v is going to equal the radius of the object times the angular velocity. So it's going to be the same exact thing as it was for linear displacement and angular displacement. Okay, so now let's look at angular acceleration. So angular acceleration, which we're gonna call A, alpha, is the rate of change of angular velocity. So it's gonna be measured in radians per second squared. And so this is going to be different from linear acceleration because it's how fast the object is changing in the rotational direction, you could say. And it's going to be different from just A because that's how fast the object is changing in that direction. Let's just say that V is going this way. So how do you get from acceleration to alpha? Well, you can probably guess by now. It's just going to be acceleration equals the radius of the object times alpha. So that's what we need to understand. So additionally, something that we should note is that for all linear kinematics equations, the rotational kinematics equations are the same exact thing, except d is going to equal theta, v is going to equal w, and a is going to equal alpha. So if we take a look at these equations, we can see that all we have to do is anytime we see a v, we have to change that to w. Anytime we see an x or a d, whatever you want to call it, you change it to theta. And anytime you see an a, you change it to alpha. So that's going to make it really easy for us to solve equations where we have to use rotational kinematics because we already know these equations, and most of these equations are on our formula sheet. So you don't have to memorize these formulas. You just have to know, oh, let me look at my formula sheet for these ones. So let's try a couple of questions. So in this question, we're given a turntable that is initially at rest, is set in motion with constant angular acceleration. That means that we can use these equations. What is the angular velocity of the turntable after it has made one complete revolution? So what do we know in this equation? Well, we know that wi is going to equal 0. We know that the angular acceleration is constant. We also know that delta theta is going to equal 2 pi because we have a complete revolution. So what we want to find is WF, right? So how can we do this? Well, what we can do is we can use our equation here, okay? We can say WF squared equals WI squared plus 2 alpha delta theta. So what do we know here? Well, we know that WI squared is 0 because 0 squared is 0. And so we know that delta theta is 2 pi. So we can say WF squared equals 2 alpha times 2 pi. So WF squared equals 4 pi alpha. So if we want to just get WF, then we can square root both sides, and we would get WF equals the square root of 4 pi alpha. So our answer is going to be C. So let's take a look at another question. So we see here the driver of a car traveling at 30 meters per second applies the brakes and undergoes a constant negative acceleration of 2 meters per second squared. How many revolutions does each tire make before the car comes to a stop, assuming the car does not skid and that the tires have a radii of 0.3 meters? So what are we given? Well, we're given that VI equals 30. We're given that A equals -2. We're given that VF equals 0. And then we're asked, what is delta theta? So there's a couple ways we can do this problem. We can either change all of these into W, alpha, W, or we can just solve this problem for D and then change it to delta theta by saying D equals R theta. So that's what we're going to do here. So we can say that delta D. So we can say here that VF squared plus V VF squared equals VI squared plus 2A delta D. So we can say that 0 squared equals 30 squared minus 4, because 2 times -2, delta D. And so we would have 4 delta D equals 900. So we would divide both sides by 4, and we would get that delta D is going to equal 225. So then how are we going to change from delta D to theta? Well, we know that D equals R theta. So we know that 225 equals, we have a radius of 0.3, so 0.3 times theta. So we can say 225 over 0.3 equals theta, which is going to equal, let's see, 225 divided by 0.3 is going to equal 750. So that's delta theta. But that's not what we're asked. We're asked, what is the amount of revolutions? We know that one full revolution is 2 pi. So if we go 750 radians, I should say, then we know that the amount of revolutions we make is 750 divided by 2 pi, because that'll tell us how many times we fully completed 2 pi revolutions. So 750 divided by 2 pi, let's see here, is going to be 119.3. So we made 119.3 revolutions.